Hi, I'm Dattner, and this is the second talk in our symposium about network structure in Semitic morphology. And here I will present network measures in the service of developmental morphological analysis. So basically, I will talk about our methodological framework. Language development is complex, dynamic, and adaptive. And this view of language development entails a growing complexity of networks between forms and functions. That is, networks of form and meaning, as well as networks between functions, such as semantic networks, and networks between forms, such as morphological networks. And this is the topic of our symposium. Dynamic relations in linguistics can be explained using network analysis, and we see it in the realm of semantic networks, where there are many studies that analyze their structure and development, but we also see studies that discuss networks in syntax or in language change, or even networks of language users. The present talk proposes a novel methodology to account for the emerging patterns of use by analyzing morphological relations as networks. So we focus on the networks between forms in the language. And specifically, we account for the relations between the Semitic constructs of roots and patterns, the Semitic constructs that Dorit Ravid presented earlier, which are the morphological building blocks of Hebrew verbs. As explained in the previous talk, we focus here on three morphological constructs. First is the root. Second is the binyan plus temporality pattern. And finally, we have agreement inflection. In the following presentations, we will see how the combinations between roots and patterns can be construed as a network, and how and what can we gain from such construals. But first, let's begin at the beginning. What is a network? A network is a system of linked nodes. So it is composed of nodes with a link between them. Networks can be found everywhere. You can see networks in the internet. So the internet is a network. We can see here a representation of the internet, which is in fact a global system of interconnected computers. And here in the graph, we can see that it is not just about the physical location, but rather about the distance between the networks. So a network can represent distance, not just about physical distance, but in terms of importance or centrality, or more basically in terms of the network structure or topology. Another example of networks is a network of social relations. So here we see social relations between universities, and specifically, this is a map showing prestige hierarchies in faculty hiring networks. And what we see here is that if you graduate from MIT, you have a bigger chance for of being given tenure in Carnegie Mellon than in Princeton. So these are the social relations between these universities. Each university is a node in the network, and we have links between them that represent something in these social relations. Another type of network is transportation network. For example, we can see here a visualization of global commercial shipping on a specific day, and we see links between ports. So each line is a shipping route of a single ship between one port over here and another port over here. And note, an interesting feature of this network is that it begins on a blank slate. As it grows and grows, that is, as ships move between one port to another, there is an emergent property of the map that shows the continent of the globe. Let's move on to another example. The brain can be captured as a network. And this is what we see here as a representation of the network architecture of the long distance pathways in the macaque brain. So we can see the links between the different lobes construed as links between nodes within the network. So basically a network, is two columns of nodes with links between them. So we can see here a very simple network with 6 nodes, A, B, C, and X, Y, Z, with several links between them. If we think about this simple network in morphological terms, in Hebrew morphological terms, as we saw earlier in the root stock, we can think of it as linking roots and patterns. So here the root PTH is linked to the pattern hitpael. And this same pattern, hitpael, is linked to the root sedere. And the root sedere is in turn linked to a pattern PL. Each link, in fact, creates a word form, a verb. So PTH and hitpael is hitpateach, which means develop. And hitpael, the same binyan with sedere, a different root, is histader, or arrange oneself. And the same root with another binyan, with PL, sidel, is to arrange. And over here we have lekeche, a different root with a different binyan, kal, which form the verb take, lakach. So we can think about the Hebrew, the links between roots and patterns in Hebrew morphology as a network. And this is what we were going to do in the next presentations. So a network is a system of relations, and network analysis is the set of statistical tools designed to study these relations. In fact, network analysis examines complex interactions between entities that belong to the same system. And so far, we talked about static networks, but we can also look at networks from a dynamic perspective, in which network topology changes over time, as we saw in the network of the global shipping, and nodes and links may come and go, as we will see in the talks about morphology in Hebrew. A dynamic model of network assumes that higher order properties are emergent phenomena. Structure emerges on the basis of the dynamic interactions between lower level components. And if we think about it in linguistics terms, the dynamic network approach is compatible with recent usage-based approaches to cognitive representation of language. For example, Bybee and McClelland, and also Kapuscinski and many other usage-based scholars argue that learning is constantly updating connection weights between nodes based on experience. And this is in fact a very similar approach to what we take in here. And other studies focusing on the development of semantic networks show that typically developing children have adult-like network structure from very early on, while children with delayed language development have the structure to a smaller degree. So linguistics analysis or linguistic analysis can be construed using network analysis. The morphological network of the Hebrew verb lexicon is dynamic, links between roots and patterns change as a consequence of the interaction with other roots and patterns among other factors. And for example, we can determine an importance hierarchy of roots or temporal patterns or inflected patterns in the lexicon as measured by their linkage to other roots and patterns. This hierarchy might have implications for further usage. Or in this way, we can also predict the probability of using a specific root with one temporal pattern over the other. So if we can determine a specific importance hierarchy in terms of what are the probabilities to use a specific pattern on a specific day, we can do it with the help of network analysis. And another thing is that over time, morphological constructs may appear or disappear, as we said earlier. It's not the case that we use every single root or binyan temporal pattern or agreement inflection in our lexicon in each and every day. And development can be seen as a dynamically changing set of networks. And dynamic network analysis allows us to model such punctuated growth, accounting for the accumulated change. For example, the probability of using a particular binyan temporal pattern on a particular day might be higher if the same pattern was used the day before than if it was not. Such projections, the one we just made here and the one made in the previous slide, can be assessed using dynamic network analysis. So how do we do it? Let's talk about network measures. There are many measures that shed light on different aspects of the data. In the following presentations, we'll focus on 4 network measures that are relevant for the modeling of the cognitive representation of morphological networks in the verb lexicon in Hebrew. 2 measures are related to the nodes of the networks. These are the morphological constructs, of course, the roots and the patterns. And these measures are degree and eigenvector centrality. And 2 measures are related to the network as a whole, the morphological system. It's the system topology or the structure. And these are the network density and the community structure. So let's remember our network from before, the simple mock network of Hebrew roots and patterns. We have 1, 2, 3, okay, 3 roots and 1, 2, 3 patterns, creating 4 different verbs: develop, arrange oneself, arrange, and take. This is one presentation of the root of the network, and the network can be also represented as a matrix. Here we can see the matrix of the network in which each node is marked for being linked to the other nodes in the network. So hitpa'el is marked as linked, as having one link with patach, peteche, and one link with the root sedere. On the other hand, the root peteche has one link only with hitpa'el and with no other binyan. So the first measure is the node degree. Node degree is the number of links a node has with other nodes in the network. So hitpa'el has 2 links and the degree is 2. Lakach, lekeche, the root has 1 link and its degree is 1. In networks that are more complex than the one we're showing here, the node degree measure can comprise both type and token frequency in a very interesting and revealing way. Next measure is the node eigenvector centrality. And eigenvector centrality is an important measure. It is a relative measure of influence in the network. And what it means is that, links for important nodes are worth more than links for unimportant nodes. So let's think about it in simple terms. If a node is linked to a node that has many links to other nodes as well, then it is more central in the network than a node that is linked to another node that doesn't have many links to other nodes as well. We can think of it in terms of search engine. For example, the Google algorithm works in a very similar way. So sites that are upper high in the Google results page have more links to other sites that in turn have more links to other sites, etc., etc. The lower you go on the result page, the less links you have to other sites that have links to other sites, etc., etc. Okay, so these are 2 measures that concern the nodes in the network, and we compare them. And you can see that we can gain different perspective from each measure. The degree measure is very straightforward. Hitpa'el has higher degree than peteche, and sedere has the same degree as hitpa'el, okay, because hitpa'el is linked to 2 nodes and sedere is linked to 2 nodes. Peteche is linked to only 1 node, and lekeche is linked to only 1 node. So peteche over here and lekeche over here has the same degree value. This is the degree. Centrality is a different measure. And here we can see that peteche has higher centrality than lekeche because it is linked to hitpa'el which is linked to CDR, which is linked to PL. However, LKH is only linked to CAL. So over here, if we look at degree, then LKH and PTH have the same degree value. But over here, if we look at eigenvector centrality, then LKH is less central in the network than PTH. Okay, so these are the measures concerning the nodes of the network that we focus on. And now we go to measures concerning the whole network. First is the network density. The density of the network is a measure of fulfilled links between nodes. It measures the proportion of observed links relative to the maximum number of possible links. So for example, over here we have a network, as we said, with 6 nodes. So each node can be connected to the other nodes. Each node can be also connected with itself. So we have 36 nodes potentially, 36 links potentially, but in actuality, we have only 8 links, as we saw earlier. So the density of the network is 0.22. Later on, we will see how we interpret the density measure. Next is a community structure. And networks can be generally sparse, but locally dense. Community structure within a network means that the network has groups of nodes that are interconnected within them. They are highly connected between the nodes themselves with few links to other nodes in the network. For example, we can detect communities on the web, representing linked sites that talk about similar topics. So for example, sites that talk about flowers will create a community in the World Wide Web. Community structure detection algorithms try to find dense subnetworks, relying on some kind of measure of similarities between nodes, and looking for sets of nodes within a network such that the proportion of links inside this set is higher than between this set and the nodes in the other set of the network. Okay, so now that we've talked about the network measures that we focus on, let's link this framework to morphological development. Let's talk about dynamic systems. A dynamic system is a system that changes through time. And the changes that a dynamic system goes through are a function of its current state. So the next state of the system is related to its current state by some growth function that needs to be determined. Using a dynamic network analysis to model development, we can thus ask, what does it mean when the network's topological structure changes over time? We can also ask whether the current network structure of roots and patterns is a function of the network structure in previous states of the network. We can also define a specific growth function for the different aspects of the network. Let's now see some examples, but remember that we're only in the second talk of the symposium, and the following presentations by Ashkenazi and Levy will provide the actual results and models. So we talked about node degree, and we said that the node degree is the links it has with the other nodes in the network. So a node with a high degree value is more important to the network because it participates in more language events. That is, a root with high degree value participates in more language events in terms of morphological, of the morphology of Hebrew. A network with high degree nodes, with few high degree nodes, indicates repeated use of particular types. It is a less variegated network, but changes in degree distribution indicate usage variation, because we can see that in time, with age, and with other factors that we'll see in the next presentations, the degree distribution changes, so different roots or different binyan patterns participate in more language events. Moving on to node centrality. Centrality could reveal those morphological patterns that act as center of gravity for verbalization. Changes in centrality of a particular pattern can be measured during development, and the centrality of roots and patterns changed through development in a dynamic, nonlinear manner, reflecting changes in discourse circumstances. And these changes are not a matter of mere frequency, but rather of the frequency of links with other frequent nodes, and of the incremental change a network goes through during development. And this is in fact a manifestation of the network as a dynamic system. Next, we have the network density. And sparse network indicates a higher level of potential productivity. And let's understand why. The potential to form new links that have not been formed before is higher if the network is sparse and not dense, if the network is not exhausted, if there are more links that can be made between nodes that have not been linked before. Because new links between roots and patterns or agreement inflections means new contexts, to use verbs, referring to more tenses or more moods or more subject participants. That is a more fine-grained aspect of the world. Density level of the network of the child may, for example, have effect on the usage of the parent, and we will see this specific prediction in the following presentations. And finally, we have the community structure, and we take communities within a morphological network to represent emergent morphological categories within the system, a set of related roots and binyan temporal patterns or inflected patterns that act as a reference for verbalization. A network with a large number of small morphological communities constitutes a dichotomous conceptual space. Such a space is challenging the travel from one community, that is one morphological category, to another. For example, if a set of roots are exclusively linked to one binyan temporal pattern, it will be harder for the speaker to achieve a conceptualization that demands the link of one of these roots with another pattern. On the other hand, a network with a small number of large communities indicates on a more coherent system with tighter structure, grouping together the different tense-related uses of a single binyan. And that indicates the consolidation of the morphological category of binyan. So to conclude, we're using dynamic network analysis, and we can, within this framework, model the development of the morphological facet of the Hebrew verb lexicon as a network of morphological constructs, highlighting its dynamic nature. And we propose that dynamic network analysis as a framework provides insights into the complex issue of language development. What's next? Following me are the talks by Orit Ashkenazi and Ronit Levy, and we will use the dynamic network analysis framework to show how the system of the Hebrew morphological verb lexicon emerges, how it gains systematic structure, how it becomes productive, and how it dynamically changes through age and usage relative to CDS-CS relations and peer interaction. Thank you very much.